Okay, we good to get started? We good to start? We good in the front over here? Good in the back? Okay, good over here. Interesting distribution. Okay, and are we good? Pull up the chat window. Are we good for people joining us on live? Good, very good. I see many yeses, so thank you for that. Okay, so let's go ahead and get started. So today we're going to cover a good amount of stuff today. We're going to cover two new analyses. The first one is dummy-coded regression, and the second one will be chi-squared, or chi-square. That is chi-squared, not chi, chi-squared. Both of these analyses are pretty similar to stuff we've covered in the past, so I think y'all should be able to pick it up pretty easily. So hopefully we'll end a little bit early today, and if you have any questions, you can ask me any questions you have with anything. But we have this lecture, and then we have Wednesday. We're going to learn more new analyses on Wednesday, and then we have our final exam and the final paper due next week. So are y'all excited for that?
Can you talk a little bit about the final?
Yeah, so was that, who said that? Yeah, okay, gotcha. Sorry, you, yeah. Okay, good, yeah. Yeah, so the final, how it's going to work is it's going to be almost identical to the homework assignments. I'm going to give you a data set, and I'm going to say, in this data set, run the appropriate analysis that would look at the relationship between job satisfaction and job performance. So if I asked that, what analysis would you run? So job satisfaction, job performance, can anyone tell me? Yeah, there you go, yeah. So you should automatically know that's a correlation, and then you should be able to run it and then give me what the result is. And then also tell me whether that result was statistically significant. Likewise, if in the data set it also had gender, and I said, can you compare whether men or women had higher job performance? What analysis would you run? Yep, you could run a ANOVA, you could run a t-test. So you should automatically know what analysis, you should be able to run it, and then tell me what the result was and whether it was statistically significant. You can take it wherever you want, yeah, yep. And you can use a computer, you can use any program you want, you can use Excel, Jamovi, or anything else. So if you like SPSS, you can use SPSS. I'll say the one thing that students tend to get tripped up on in the final is because the guides are available. I think sometimes students think that they can just pull up the guides and just copy the guides as they go along. The final is going to be a lot of questions. So every semester, and this is no exaggeration, there's usually 2 or 3 students who get like a 20 because they don't review, they don't know how to do the analyses, and then they get to the exam and they can do like 2 within the time limit by following the guides. But you need to study and you need to know like how you can do these analyses and how you can do them quickly.
Are we going to have a review day for it?
No review day. No review day. Yep. Nope. That got scrapped this semester. So
Is it cumulative?
it will be cumulative since the midterm. So I guess the answer is no. Yeah.
If we can do the homework, it should be not, I don't think it's easy, but we should be able to follow.
Yes.
The rest of the final.
So if you can do the homework, you'll be able to do most of the final. The 2 things I'll say is make sure you can do the homework like quickly. So if it took you like hours to do a homework assignment, you got to get quicker on that. The other thing I will say is that there's going to be like 2 or 3 analyses that we'll cover in the class that will not be on a homework assignment. You still have to know those analyses. So for instance, these 2 analyses are not going to appear on a homework assignment, but you still need to know them for the exam. So.
We didn't have any quadratic regressions in homework.
Nope, you did not.
So we won't.
They could be on the exam. Yep. So anything we cover since the midterm could be on the exam. Yep. Another thing I'll note is if you want more practice, if you go to maxihoward.com and look at like the Jamovi stats pages, if you scroll down, there's a bunch of practice examples. So anything we've covered in this class, there's tons of practice examples on maxihoward.com. So. What day is the exam on? Monday. Yeah, the exam is Monday. Yep.
Okay.
Yep. Yeah, final papers due Wednesday, exam on Monday. So. I'll probably give you 2.5, I'm assuming. Yeah, I'll probably give you all 2.5. Yep. So, sorry, what's that?
The data set be rearranged.
Oh, that's a good question. So the question was, will the data sets have to be rearranged It depends on what program you're using. Because some of the questions, the data might be arranged to fit like Jamovi. So if you're using Excel, you'll have to rearrange it for Excel if you're only using Excel. So the answer is depending on the program.
So if you plan to use Jamovi all the time, it should be.
I'm not going to guarantee that. Yeah. So because I might have some things formatted for Excel, but then you'll have to reformat for Jamovi. Yeah. So good question. Trying to think. I feel like there's another comment I was going to make. Oh yeah, so homework 3 and 4, I'll talk about it briefly today, but I should make those available to review tonight. There's one student who had to turn it in late, so once that student turns it in, I'll make it open for y'all to review. Are y'all okay, by the way? Y'all good? Okay. So homework 3 and 4 will be available to review hopefully tonight. I will try to make homework 5 available to review ASAP after it's due. Like I'll try to make it available Sunday night because that's when it's due. So you should be able to look at the answers Monday before the test. And yeah, so that means on homework 5, you can't turn it in late. You cannot turn in homework 5 late because the exam is within 24 hours after that. So if you have something come up, like you got to let me know ASAP to figure out a solution.
Relatively, like, how much is going to do on homework 3?
I'll cover that in like 3 minutes. Yep. Yep. Is that what? Yeah. So someone asked about that too.
I just don't know, like, I know I missed 2, but
Yeah.
genuinely don't know how I missed 2.
Yeah. And I'll open it up so everyone can look at their answers and the correct answers once that final student turns in their submission. So we'll like talk about it briefly today, but then after today, you should be able to review it and see what you missed. Yeah. So, okay. Any other questions or comments? Anything else? Yeah. Oh, you're good.
On the final, will there be any, like, conceptual questions from like, the PowerPoint, like, just like questions about the programs or anything?
That's a good question.
Instead of just like running the database.
So everything you'll have to be able to run the analysis, so get numerical results. You'll definitely have to interpret p-values. So that's one thing I'll say to the entire class on the homework assignments. I was surprised at how many students missed that, where you would say like my p was less than 0.05, therefore it was not significant. Like, no, you got to know that better. That's going to be a huge part of the exam. There will not be any conceptual questions though. So there will not be any conceptual questions. So you will be expected though, like I said, if I tell you to figure out the relationship between two things, you'll have to conceptually know what analysis answers that question. But there's going to be no questions like, even though we didn't cover this in this class, there's not going to be any questions like what is heteroscedasticity? Like nothing like that. Yeah. Exactly correct. Yep. So, okay. Any other questions or comments? Okay. There are 2 questions from last class. So first off, that's what we're covering today. I already said that. There are 2 questions from last class that came up, and I said I would answer them today. The first one is if you're looking at the GADs have different post hoc tests depending on if you're doing a one-way or one-factor or two-factor ANOVA in Jamovi. So I went back and double-checked that, and that is correct. The reason why is in Jamovi, if you're doing a one-factor ANOVA, you can do a post hoc test that's really good that avoids a lot of problems. However, that post hoc test is not available for a two-factor ANOVA. So the only thing you need to know is the guides are correct. So if you've been using the guides to figure out how to do a one-factor or a two-factor ANOVA, you're good. Keep using them, keep doing what I said. I just wanted to clarify that that's why the post hoc tests are different, is because the better post hoc test you can only do for one-factor ANOVA. It's not available for two-factor ANOVA. So the other question was someone asked, what does the T stand for in t-test? And I knew most of this background information, but I didn't know the very last point, so I'm glad someone asked this. So the background information is a t-test. A person named Gossett formalized a t-test. Some people say he invented it, but we tend not to really invent things in stats. We just kind of.
That's not what we should.
Exactly. Exactly. No, this was invented in like 1908, I want to say. So this person invented a t-test. Gossett, even though his name was Gossett, when he published the article, he called himself student, and that's because he was working for Guinness, like yes, that Guinness company. He was working on conducting statistical analyses to make better beer. So he published a paper, called himself student, because Guinness wouldn't let him use his real name. So when he published the paper, he talked about the student distribution, the student's test. At the time, there was already S distribution for standard deviation, and he thought if he called it an S test, people would assume it's a standard deviation test. So he just used the next letter in student, which is a T. So that's why it's called a t-test, because that's the second letter in student. So whoever asked that question, thank you for asking it, because I knew that Gossett worked at Guinness. I knew everything else. I did not know that it's a t-test because it's the second letter in student. So I learned something new from that. So, okay, interesting stuff. Are there any, we'll go over homework now. So someone asked, how did y'all do on the homework? The answer is y'all did extremely well. Y'all did extremely well. I think on average, people missed 2 questions on average. So y'all did really well. It was straightforward apparently. Average grade was a 92.5. When you ran the correlations, and this is in the PowerPoint, so if you want to double check your answers to this early before I release it tonight, you could. So I guess the one student who still has to turn it in. Okay. Hopefully that person's not watching this, but if you are, try to be honest. I don't know what to do now, but it's too late. So this was the correlations and the Cronbach's alphas. Everyone was able to do Cronbach's alpha. I don't think there's a single person who missed a Cronbach's alpha question, so give yourself a pat on the back about that. Those are the correlations. The things you should have noted was purchase regret did not significantly predict repurchase intentions, whereas satisfaction and disappointment did. One thing I will say, and this was not something you should have noticed because I didn't ask this question this semester, but some of these correlations are really weird. Normally I tell the class to write up a report about these results, and if you were to write up a report, you probably would have noted that it doesn't make any sense that repurchase intentions is positively correlated with purchase regret, positively correlated with disappointment, and negatively correlated with satisfaction. So long story short, if this was a real semester, if this was a semester where I was asking you to write a report, then you would have noted that some of those correlations look a little bit weird, but since I didn't ask you to write a report this semester, you're all good if you just gave the right numerical answer. Then you should have ran independent regressions where there's just one predictor. These results are pretty much the exact same as the correlations. Regret was not significant, whereas disappointment was borderline, it came really close, and satisfaction was statistically significant. And then you should have finished it by running your regression with all 3 predictors, and this is what it would look like. And when you put all 3 of them together, both satisfaction and disappointment were significant predictors, whereas regret was not a significant predictor. So once again, the results were pretty consistent throughout. The things that were significant with the correlation were still the things that were significant when you ran a regression. But it's good practice. It's good practice to run all these different analyses. And then we had homework 4. Once again, almost everyone got an A on this, so good job. Give yourself a pat on the back if you're one of those students. The average grade was above a 94, so this was apparently too easy. As you saw, the group means were this. There's group 1 and 2 had a mean of around 5, group 3 had a mean of 10, and group 4 had a mean of close to 20. So the groups were different in their means, except for 1 and 2 were very close. All the others were far apart. When you ran a 1 sample t-test, you found the groups 1, 2, and 4, their means were significantly different than 10. And then when you ran a 2 sample t-test or a series of 2 sample t-tests, each group comparison was statistically significant, except for the comparison between groups 1 and 2. Because those were the 2 groups that had means of about 5, so it makes sense that they were not significantly different, whereas every other group comparison was statistically significant. Likewise, for the 1 sample t-test, group 3 had a mean of really close to 10, so that makes sense that group 3 was not significantly different than a value of 10, whereas all the others were significantly different. Okay, so that was a very brief summary of the homework. Were there any questions or comments about it? And once again, this should be available to review tonight. That's my goal. Any questions or comments about anything in the class? Going once, going twice. Okay, so if there's no questions, let's go ahead and let's start the lecture. And we're going to start today by talking about dummy-coded regression. We're starting by talking about dummy-coded regression. Okay, so this is the chart we've been going back through all semester. However, there's one difference. There is now one difference with this chart. There's one thing that's added, and that's at the very top. So all throughout the semester, we've said the first thing we should ask ourselves when doing statistical analyses is what are we investigating? Are we trying to explain the relationship between variables, or are we trying to look at the difference between groups? That's what we've been saying all semester. Is it the relationship between variables or the difference between groups? And as you see for this lecture, we have another one added, and that is both. That is both. So as you can see very clearly, dummy-coded regression is used when we're trying to look at both the relationship between variables and the differences between groups at the exact same time. So once again, dummy-coded regression is when you're trying to look at the relationship between variables and the difference between groups at the exact same time. So that's what that says. So this is different than regression. Typically, regression is simply just used to look at the relationship between variables. So this is a special instance of regression. This is a special instance of regression. This is an instance of regression where we're both looking at the relationship between variables and the difference between groups. So one question you can answer with dummy-coded regression, is what's the difference between training groups on performance, and what's the relationship between conscientiousness and performance? So what's the difference between training groups on performance, and what's the relationship between conscientiousness and performance? So can anyone tell me first off, in that example, in that question, what's the difference between groups we're looking at? What is the difference between groups we're looking at? Exactly correct. So first off, we're looking at the difference between groups by looking at the difference between the training groups, by looking at the kind of training. So we're looking at the difference between training groups based on their performance. So we're looking at the difference between training groups on their performance. So we have a grouping variable and we have a different measured outcome variable. So typically if we're running analysis, we're look at that. Typically we might be using a t-test. In this case, we're not, but typically if we just wanted to look at that research question, we would be using a t-test.
Yeah.
But this time we're not. This time we're using dummy-coded regression because we have
It made it worse.
So this time we're using dummy-coded regression because we also want to answer this second
For some reason, she decided that that would also be a good time to go ahead and inform me that I'm not getting as much movement on an internal project that I'm heading up, and that she's going to give it to somebody else. And
exactly.
she apparently.
So Colton, you need to put yourself on mute apparently. Colton online. Okay. So Colton, if you're hearing this, put yourself on mute. There you go. Thank you, Colton. Okay. So to continue, the relationship between variables we're looking at is conscientiousness and performance. So just like we would look at with a normal correlation or a regression, we're looking at no, that's terrible. We're looking at the relationship of conscientiousness to performance. But we're also looking at the difference between groups in regards to the training groups. One thing important to note about this is for both of these research questions, we have the same outcome variable. For both of these research questions, we have the same outcome variable. The outcome variable being performance. So we're looking at the relationship between conscientiousness and job performance, as well as training group and performance. So to do a dummy-coded regression, we have to be looking at the difference between groups, and we have to have a separate measured outcome variable. That's a minimum. So at a minimum, we have to be looking at this difference between groups and a separate measured outcome variable to do dummy-coded regression. This is at a minimum. But then on top of that, we could add other variables. We could look at other relationships, such as the effect of conscientiousness, but we have to look at it regarding the same outcome variable. So once again, to do dummy-coded regression, we have to be looking at the difference between groups in regards to the outcome. And if we want to model the effect of other variables, we have to look at the effect of those variables on the same outcome. Okay. So therefore, in doing this, one thing that's very useful is in addition to being able to look at multiple relationships in the same analysis, we also get to look at the effect of one while controlling for the other. We get to look at the effect of one while controlling for the other, and vice versa. So therefore, in this example, we can look at the effect of training group on performance while controlling for conscientiousness, If we think for some reason that this relationship between training group and performance would be biased by our trainees' initial conscientiousness, we can measure this, and then we can later do a dummy-coded regression and look at the impact of training group on performance while controlling for conscientiousness. And dummy-coded regression will let us do this. Because it's just simply regression in a certain context, a certain special instance of regression. So it still abides by the same rules of regression, but it still looks at the relationship of each variable on the outcome at the same time. And therefore, by doing that, it controls for the effect of all the other predictors. So therefore, by doing that, it controls for the effect of all the other predictors. So we get to look at the effect of training on performance while controlling for conscientiousness, but also conscientiousness on performance while controlling for the effect of training group. Okay. Any questions about that so far? Okay. Yeah. So how this works is dummy-coded regression lets us test the mean difference between groups using regression, and to look at and see how this would work statistically, but also how you would see it in a computer program. We're going to start with the easiest example, and we're just going to look at regression to analyze the difference between two groups. Like I said, to do a dummy-coded regression, you have to at least have the difference between groups you're looking at in regards to an outcome. And we're going to start with that because that's the easiest instance of dummy-coded regression. So just simply looking and seeing via regression, is there a difference between two groups? And once again, although we would typically use a t-test or an ANOVA to analyze this question, it could be done by dummy-coded regression by itself. So how this would look like statistically, our data set would need to have two variables. The first one would have to be our outcome, and the second one would have to be a variable representing our groups. The second one would have to be a variable representing our groups, or our grouping variable. However, our grouping variable needs to be coded as 0 and 1. Whereas when y'all did a t-test, some of these stats programs will let you keep it as something like Dr. Howard and Dr. Smith, or male and female. When you're doing dummy-coded regression, you have to recode it as 0 and 1. That's extremely important. It's also important you choose 0 and 1 because otherwise you might get different answers. That's not to say that they're incorrect, they just have different interpretations. So we're learning about dummy coding. Dummy coding is when you explicitly code it as 0 and 1. Another option would be effects coding. Effects coding is when you code it as -1 and 1. That's just as correct. It would just result in a different interpretation. And once again, that's called effects coding. When it's -1 and 1, that's something slightly different. We're learning about dummy coding, which is explicitly coding it as 0 and 1.
Can you back up from slide?
Yep.
So how do you learn at the same time? You don't want to do the whole thing to
We'll look at that in a few slides. Yep. All right. So ask that again in a few slides if I don't answer that. Yep. Okay. Are we good to move on, or?
Yeah.
So question was, does it matter which one is 1 and which one is 0? The answer is no, as long as you remember which one you coded as which. So the short answer is no. The short answer is no, it doesn't matter which one is 1 and which one is 0. When you're only looking at two groups. In a few slides, we're going to get to when you're looking at more than two groups using dummy coding. And in that case, it does matter. Which one is 0 and 1. So the short answer is when you're only looking at two groups, it doesn't matter. When you're looking at more than two groups, it does matter. So very good question, and we will talk about that more in a few slides. Okay. So once again, you should code your groups as 0 and 1. So therefore, your data set might look like this. And in this example, we have our participants. So this is a small data set of just participants 1 through 10. And the grouping variable is whether they're a full-time employee or whether they're a manager. So whether they were a full-time employee, let's say hourly employee, or whether they were a manager or salary employee. And then we have an outcome variable that might be something like job performance. So then we have an outcome variable that might be something like job performance. So based on that, if we were doing a dummy coded regression, the very first thing we would do is we would create a dummy variable where we recode all the full-time employees as 0 and all the managers as 1. So we're just recoding it as 0 and 1. Typically, you want to recode it as a new variable. You don't want to move. What? All right, I'll pretend that never happened, I guess. That wasn't anything important, was it? Could y'all understand what it said? Is it next door? Okay. So if it doesn't happen again, we'll ignore it. I thought it was like an emergency announcement. Yeah. So okay. All right. Okay. So anyways, back to this. Typically, when you're dummy coding, you do not want to overwrite your the name of your variables. You do not want to overwrite. You want to make your dummy code in a new column, so that way you can quickly look at your data set and know. All right. So obviously, full-time is 0. That means that my dummy code is formatted that way. Manager is 1. So you do not want to overwrite your old variable. Okay, so then after making your dummy code, all you're going to do is you're going to run a regression, and you simply just have your outcome as your y variable. You just have your outcome as your y or your outcome variable, and you have your dummy code as the predictor or as the x. So it's very simple. The dummy code is a predictor. It's your x. And then you just put in your outcome as the outcome, which is the y. And you're going to get results that look like this. You're going to get results that look like this. So without knowing anything else about dummy coding at this point, can anyone tell me whether this tells us there's a significant difference between the groups? So based on this result, would you assume that there is a significant difference between the groups?
Yes.
And why'd you say yes?
Because of that asterisk.
Exactly correct. Exactly correct. You interpret this just the same as regression, that if the asterisk or the p-value associated with your dummy variable is statistically significant, then that means there's a significant difference among the groups. That means there's a significant difference among the groups. So once again, we're interpreting this just the same as regression, that if your p-value associated with your dummy variable is statistically significant, that means there is a statistically significant difference among your groups or between your two groups. And then also based on that, you can interpret your betas. So depending on how you coded your groups, 0 or 1, if you coded it 0 as 1 in this example with full-time being 0 and manager being 1, if your beta is positive, that means the managers had the higher values because they were coded as 1. So if you coded it 0 full-time, 1 manager, and it turned out to be positive, your beta was positive, that means the managers had the higher outcome variable. On the other hand, if your beta was negative, that would mean that the full-time employees would be higher on the outcome variable, depending on how you coded your 0 and 1. I will say just the easiest way to know what your groups look like, though, is I would say just run this analysis. If you're statistically significant, if your result is statistically significant, just calculate the means for the two groups. Just calculate the means for the two groups. And that will show you which group is higher. That will show you which group has higher values. Okay, so then from this, we can just add other variables to the regression to analyze their impact in addition to the grouping variable. So from here, we started with this just basic one. We're looking at the impact of the grouping variable on your outcome. If you then want to see the impact of other variables, you just add them to your regression. So to go back to the original example, we have the training groups, we have performance as the outcome, and now if we wanted to analyze the impact of conscientiousness on our outcome, we would just simply add that to our regression. We would just add that to our regression. And that would be no different than conducting a normal regression. That would be no different than conducting a normal regression. We've already looked at regression where we look at conscientiousness and performance, things like job satisfaction and performance. We just include that in our regression at normal. And because this is already dummy coded, because training is already dummy coded, we can just include this in our regression and it will work very easily. Okay. So based on this result, how would we interpret this result? Anyone tell me what this result is telling us? Say it again a bit louder. So first off, there is a significant difference among the training groups because we see the dummy variable row The p-value is statistically significant. So we say there is a statistically significant difference among the training groups in regards to the outcome variable of performance. What's the other thing you should say about this result? Let's ignore the betas for now. Good point though, but let's ignore them. What's the other thing you should say about this result? We'll ignore the words for now. One more thing you should say about this, or one more thing we could say about this. So we know there is a difference among the training groups in regards to performance. What's the other thing you can say about this result? Not a difference. You're on the right track. Does anyone want to take the baton and go across the finish line? There you go. Yeah, that there's a significant relationship between consciousness and performance. And that's the interesting thing about dummy-coded regression. Is dummy-coded regression can look at the difference between groups in regards to performance, but it can also just look at the relationship between variables in regards to the outcome. So in this example, we saw that there was a statistically significant difference among the training groups in regards to performance, but we also see that consciousness had a statistically significant relationship with performance. So based on this result, if my marker could draw on, we would say that there was a difference among the training groups in regards to their job performance, but also conscientiousness had a significant effect on job performance. Conscientiousness also had a significant effect on job performance. So once again, testing the difference between groups in regards to an outcome, but then also looking at the relationship of a variable on the outcome. And this analysis does both at the same time. Any questions about that? Comments about that? Okay. So why does this work? Why does this dummy-coded regression thing work? So very briefly, this is the simplest way to explain it. So if you're thinking about a t-test, we talked earlier in the semester, that you're thinking about bars. You're thinking about a bar chart. So a t-test looks at the difference between two groups, and it looks at the difference between the means of these two groups. So if you're thinking about this on a bar chart, it's looking at the difference of the heights of the two bars. Typically, a bar chart, the height of the bar represents the mean. So if you're doing a t-test, it's comparing the mean of the two groups, or it's comparing the height of the two bars. When you're doing a dummy-coded regression, it forces a regression framework on this type of research question. And you can still think of it as a scatter plot. We talked about how regression is a scatter plot. You can still think of it as a scatter plot, except, draw real quick, except instead of they should change the numbers to be more correct. It forces a regression framework where you have a 0 and you have a 1 right here. So it forces a regression framework on that on the grouping variable, where all the observations for one grouping variable is going to be at the 0, and all the observations for the other grouping variable is going to be at the 1. So what it does is it forces a regression framework, and it still draws the line of best fit where the data points lie. So therefore, if the line is a steep slope, it's more than likely to be statistically significant. And for it to have a steep slope, there needs to be a greater difference between the groups. So how this works is, as you remember with regression, if your line has a steeper slope, it's more likely to be statistically significant. So therefore, if there's a difference in the height of the bars, if you're forcing a regression framework on it, then therefore it's more likely to have a steep slope. So therefore, it's more likely to be statistically significant. Or on the other side of the coin, if you had a bar chart that looked more like that, and you tried to force a regression framework on it, and you drew a line of best fit, it would probably look closer to that, and that's probably not going to be statistically significant. Because your line does not have a steep slope, it has a very flat slope, and it's because the two groups have similar means and their bars are equal height. So therefore, that's how dummy-coded regression works, is it forces this regression framework. You can think of it as just, if I were to draw a line of best fit through the mean of the two groups, would it have a steep slope or would it have a pretty flat slope? And that's how this dummy-coded regression works. So someone asked, how do you interpret the beta on slide 24? So I will go back then. So someone asked, how do you interpret that beta? Let's just focus on the standardized beta, or let's just focus on the direction. So the beta for the dummy variable is right here. So if it's positive, if your beta for the dummy variable is positive, that just means that whatever group you had coded as 1, that's going to be the group with the higher mean values. So once again, in your beta, how you interpret it is if you're looking at the dummy variable beta, and we're just going to think about direction right now. If you're going to look at the dummy coded variable, if it's positive, whichever group you coded as 1 is going to have the higher outcome variable. So if this was group A and B on job performance, and A was coded as 0 and B was coded as 1, then this would mean that B was higher on the outcome variable because B was coded as 1. On the other side of the coin, if this was a negative beta right here, if this was negative, then that would mean whatever group you coded as 0 was higher on the outcome variable. Whatever group you coded as 0 was higher on the outcome variable.
So you're always looking at one to give you the direction on whether it's positive or negative.
If you're always looking at 1, that's one way to put it, yeah. I mean, you could put it the other way, you're always looking at 0. It just depends on how you code it. So, and we also see that, maybe this will help too. We can also see that in this picture right here. We also see that in this picture right here. That as we see here, the line of best fit is negative. The line of best fit is negative, and if I were to number this axis correctly, it'd be 0 and 1. So this regression line is negative. So therefore, that means that the zeros had higher values on the outcome than the 1s. And we see that right there. So I hope that answered the question in the chat. Does anyone else have any questions or comments about this? Okay. Okay, so moving forward. Also, the last thing we'll talk about dummy coding is we can use dummy coding to look at more than 2 groups. We can use dummy coding to look at more than 2 groups. And it would look like this. So in this example, we have 3 groups. In this example, we have 3 groups. And in this example, if we have 3 groups, we would make 2 dummy coded variables. We would make 2 dummy coded variables for 3 groups. And whenever you have more than 2 groups, in this case 3 groups, you have to determine which group is going to be 0 for all the dummy coded variables. You have to determine which group is going to be 0 for all the dummy coded variables. And then for dummy code variable 1, one of the groups has to be a 1 and all the others is 0. And then for 2, that last group has to be 1 and all the others are 0. The reason why it's important, though, to determine which group is going to be all zeros across all the dummy coded variables is because the group that's all zeros, that's your comparison group. The group that is all zeros is your comparison group. And that's extremely important. The group that is all zeros is your comparison group. So when you are to run your dummy coded regression, when you have more than 2 groups, let's say in this example, we have dummy variable 1 and 2, this full-time employee group is going to be your comparison group for all of your dummy coded analyses. It's going to be your comparison group for all of these dummy coded analyses when you run your regression. So therefore, it compares your comparison group against whatever group is coded as 1 for that dummy coded variable. So it compares your comparison group for whatever group is coded as 1 for your dummy coded variable. So when you run your regression, this dummy variable 1 is going to represent the difference between your comparison group, full-time employees in this example, and your managers, because in this variable, you coded your managers as 1. In this group, we have dummy variable 2. We still have full-time employees as the comparison group. However, now part-time employees is the one coded as 1 for this dummy variable. So therefore, your results regarding dummy variable 2 is going to be the difference between part-time employees and full-time employees. Once again, because full-time employees is a comparison group for all your dummy codes, and then part-time is the one you coded as 1. So therefore, if you were to run your dummy coded analysis with this, your 2 dummy variables would represent the difference between group 1 and group 2, as well as group 1 and group 3. So therefore, it's important to determine which group you want to make your comparison group. Because we could recode this and make the managers your comparison group. We could recode this and make the managers the comparison group just by making them 0 here and changing these to 1s. we could simply do that and make your managers the comparison group. Someone asked in the chat, can you compare all three or only two at the time? In this example, if you have three groups, you can only compare two at a time. If you have only three groups, you can only compare two at a time. The reason is because if we added a third dummy variable, where full-time employees were coded as 1 and everyone else was coded as 0, for instance, you would get an error. You get an error in your analysis. It just wouldn't work because the three variables would be completely codependent on each other. It wouldn't work. You will get an error. So therefore, you can only make two.
There's a limit to using dummy.
Sorry, what's that?
There's a limit using the dummy code.
You say, is there a limit?
Yes.
And what, like, how many groups you can have?
Well, like, in this instance, there's a limit. Are there other instances where there's not?
There's many ways to interpret that. So the question was, is there a limit to dummy coding analysis? There's no limit to the number of groups. So if you had 50 groups, you could throw in 49 dummy codes. That's completely fine. So there's no limit to the number of groups you can compare with dummy coding. There's just a limit in the sense that, like, you can't make, so whenever you do dummy coding, you have to choose your comparison group. So therefore, it's comparing your comparison group to all the other groups. You can't then also then compare, like, these two by a dummy coded analysis. So there is a limit in that regards, as it can't do every single comparison like an ANOVA can, but it doesn't have a limit on the number of groups that you can have. So good question. Okay. And then, yeah, and I think I answered that in the chat. You cannot compare all three. You can only compare your comparison groups to all the others when running it. So someone asked, can SPSS allow you to compare more than two groups? So any stats program, you can compare more than two groups. So if you did Excel, if you did SPSS, if you do Jamovi, you could run this because this is comparing more than two groups. None of the programs, though, are going to let you compare more than just like the comparison group with all the other ones. So even if you're using SPSS in this example, you couldn't run one dummy coded regression and compare full-time employee, manager, full-time employee, part-time employee, as well as manager and part-time employee. You still couldn't do this comparison with one dummy coded regression. But no matter what program you're using, you can't have more than two groups. You just can't make all the comparisons possible with one analysis. So, okay. Other questions about dummy coded regression? Any other questions?
I guess if you want to compare multiple groups, you have to decode the table.
That's correct, yeah. So if you did want to make, like, you could run multiple dummy coded regressions. You certainly could. That would just require multiple analyses, and therefore some of the group comparisons would be independent. And you tend to want to avoid that. Yeah. So, any other questions or comments? Okay. Good questions, though. Very good questions. Okay. So in this example, we have dummy variable 1 and 2. Full-time is coded as 0. Yeah, full-time is coded as 0. Manager 1 and variable 1. Part-time and variable 2. Yeah, that says it on the PowerPoint. So if this is a confusing concept, it's restated on the PowerPoint for you to review if you want to. And there it is again. So then we might run a regression and we include those two dummy variables in there. So looking at this regression, what are these results telling us? What are these results telling us? So those.
If I buy some more markers, can I get extra credit?
Exactly. There we go. I would say yes if this one didn't work, so you're very close. Full-time equals 1, manager, sorry, it was full-time equals 0, manager equals 1, part-time equal 2, or sorry. Dummy variable 1, dummy variable 2. Okay, that's how it's coded. Full-time was 0 for all the dummy variables. Manager was 1 for dummy variable 1, and part-time was 1 for dummy variable 2. So based on this result right here, how would you interpret that? How would you interpret this result? So first off, the differences are significant. So let's take it a step at a time. So what is dummy variable 1 comparing? Yeah, you got it. Yeah, exactly. So dummy variable 1 is comparing full-time to managers. So dummy variable 1 was statistically significant. So the comparison between full-time and managers, that's statistically significant. So first off, we know there is a significant difference based on this result, because we see the p-value associated with dummy variable 1 is statistically significant. So the comparison between full-time and manager, that is statistically significant. So what's dummy variable 2 telling us? What is dummy variable 2 telling us? Yeah, exactly, full-time and part-time. So it's looking at the comparison between full-time and part-time. And is that statistically significant? Yes, yes it is. Because we see 2 asterisks, that means the p is less than 0.05 for dummy variable 2. So this result is telling us if we were to run this dummy coded analysis, that the relationship, or sorry, not the relationship, the difference between full-time and manager was statistically significant, and the difference between full-time and part-time was statistically significant regarding whatever outcome we're looking at. This might be job performance, let's say. We can also, like we talked about before, look at the betas. We see both of these betas are positive, and since we coded this as 0 for full-time and all the analysis, we know that since this is positive, whatever we coded as 1 had the higher values. Because it's positive, whatever we coded as 1 had the higher values. So therefore, we said it would say the difference between full-time and managers was statistically significant, with managers having a higher number on the outcome. And also the difference between full-time and part-time was statistically significant, with the part-time having the higher values on the outcome. But also, like I said before, if that trips you up, I would say just look and see if the comparisons are statistically significant. And then if they are, just calculate the means for these 3 groups. And that should make it very clear which ones are higher, because the means might be something like 2, 10, and 10. And you can very clearly see this one was smaller than these 2, and that difference was statistically significant based on our dummy coded regression results. Okay. Any questions about that? Any comments about that?
Will all of this be on final?
There is a good chance it would be. Yes, there is a good chance.
Is there a speculation in our data? The other one where you have to select that with a movie or?
Are you talking about encoding your data? Yeah. The guy.
No, to the data, because in one of the steps, one of the data.
I see what you're saying. Yeah. So in Jamovi on the guide, this should tell you how to standardize the data. I'll assume, or how to get the standardized data out. Yeah, this should. So if you're using Jamovi, you can ask Jamovi to give you the standardized coefficients, and the guide should tell you how to do that, because it does it for regression. I'd be very surprised if I didn't include it for regression. Any other questions or comments? Okay. Is dummy variable 2 comparing part-time and managers or part-time and full-time? Yeah, so good question. So dummy variable 2, we'll go back. Let me draw. So the question was, is dummy variable 2 comparing part-time and managers or part-time and full-time? So because we had full-time is always 0, that's always going to be one of our comparisons for each of our dummy variables. So full-time is always going to be one of our comparisons for our dummy coded variables. And then we look at dummy variable 2, and we see that part-time was 1. So therefore, dummy variable 2 is comparing part-time employees with full-time employees. The dummy variable 2 is comparing part-time employees with full-time employees. So good question. So this is dummy variable 1, and this is dummy variable 2. Yep. Okay. Okay, and that is all for dummy coding, unless there's any questions. All right, so let's keep going. We're doing good on time, so let's just keep going. And now we're going to look at chi-squared. Okay. So chi-square is the last part of this chart we've been going through all semester, or half the semester. So chi-square is the last part. So chi-square is we're still looking at the difference between groups, but now we're gauging our outcome in a different way. So far, when we've been looking at the difference between groups, we've had a separate measured outcome variable. We had something like job performance, we're looking at the difference between training groups on job performance. We've had something like gender and looking at the difference between genders on job performance. Now, however, by looking at chi-squared, our outcome is going to be the number of members in those groups. Our outcome is going to be the number of members in those groups. So now with chi-squared, we're still looking at the difference between groups, but instead of having a separate measured outcome variable, we're now looking at the number of members in those groups. Okay. So the textbook definition for chi-squared is it's used to investigate whether the distributions of categorical variables differ from one another. Another way to put that is it's used to test whether the number of people within the groups of a grouping variable significantly differ. It's used to test whether the number of people within the groups of a grouping variable significantly differ. So some examples of when you would use a chi-squared, or questions you could answer with chi-squared, is in our sample, do we have more males than females? In our sample, do we have more males than females? Because in this example, we have a grouping variable, which is gender, and we're comparing whether we have more males or females in our sample. So we're looking at the number of people within each of those groups. So once again, looking at a grouping variable, gender, we're comparing the number of people in those groups. You might also have a sample and you can ask, do we have more people under 40 or over 40? Once again, age is our grouping variable. We dichotomized age. So age is our grouping variable. And we're looking at the number of people in those groups. Do we have more people under 40 or over 40? We could also get a sample and look at their hair color, and then ask, do we have more people with red hair than brown or black hair? So our grouping variable is hair color, and we're comparing the number of people in those groups. I do want to point out that the first two, there were only 2 groups. This third one has 3 groups. So you could do a chi-square test if you have more than 2 groups. You could do a chi-square test when you have more than 2 groups. So you do a you can do a chi-square test with any number of groups. So it doesn't have to be 2. It can be any number of groups. And the last example is we could get a sample and we could ask, do we have an equal distribution of people with the following car colors, yellow, black, blue, red, or brown? So we get a sample, ask them what their car colors are, then we could see, do we have more people with a certain color of car, or is it a relatively even distribution throughout? Or is it a relatively even distribution throughout participants within those groups? And so when performing a chi-square test, our null and alternative hypothesis are usually, so the null is that there's an equal distribution of participants, and our hypothesis is there is not an equal distribution. So therefore, whenever we're doing a chi-square test, let's say it's 2 groups and we have 20 participants, the null would be that it looks something like 10 and 10. So doing a chi-square test, we have only 2 groups with 20 participants total. The null would be 10 and 10. Therefore, our hypothesis, or our alternative hypothesis, is anything other than 10 and 10 for this example. So once again, for this example of 2 groups with 20 total participants, the null is its even distribution, it's 10 and 10. The alternative, or our hypothesis, is that it's anything other than 10 and 10. It's anything other than 10 and 10. And you could change that however you wanted. It could be 3 groups of 30 people. The null would be an equal distribution. Our hypothesis is something other than an equal distribution, an unequal distribution. So therefore, there's another example. Once again, 3 groups. We have a total of 30 people. The null hypothesis is that there's an equal distribution throughout. Okay. So if I were to then conduct, without doing anything else, a chi-square test on this data set right here, a data set where we have factory A, B, and C, with 10 people representing each factory, if I ran a chi-square test on that, would it be statistically significant? Would this be statistically significant? See, no. Any other people want to join in? I hear another no, and y'all are correct. It would not be statistically significant. Because our null hypothesis is that there's an even distribution. But this was our data that is an even distribution. So if we were to run a chi-square test on that, we probably couldn't reject the null. We probably couldn't reject the null. Because the null is that there's an even distribution. So therefore, if we observe something like that, that's pretty even. So we probably wouldn't be able to reject this null. All right, here's another example. So this is the same number of participants. We still have 30 participants, but this time it's 5 in group A, 5 in group B, and 20 in group C. If we're to run a chi-square test on this, do y'all think it would be statistically significant? I see one person saying yes, I see 2 people. We'd have a much better chance. We'd have a much better chance. Because this is the null, it's even. Our observation isn't that even. It's pretty, it's a little bit far from even. So therefore, we would have a good chance of rejecting this null and supporting our hypothesis is that it's something other than an even distribution. It's something other than an even or uniform distribution. Because this is pretty distant from being a uniform distribution. Okay. So therefore, that's a chi-square when you only have one grouping variable. So that's chi-square when you only have one grouping variable. And that would tell you whether you have an unequal distribution across one variable. However, you can also run a chi-square when you have multiple grouping variables at the same time. And this is similar to ANOVA in this regard, is that you can run a chi-square when you have multiple grouping variables at the same time. And you can also test for interaction effects. So like we learned with ANOVA, you can also test for interaction effects with chi-square. So you can look at multiple grouping variables at the same time, and you can also test for interaction effects. See if I can erase this properly. Okay, so there's that. Okay. So therefore, we might run a chi-square for this. So we have factory with 3 groups. We have gender with 2 groups. So that makes a total of 6 combinations. That makes a total of 6 combinations. Because we have factory with 3 groups, gender with 2 groups. And in this case, our null hypothesis would still be an even distribution across all those groups. That both would be even in regards to gender, so both 30 and 30. Even in regards to factory, so both 20, 20, and 20. But it also, the null hypothesis for the interaction effect would be an even distribution in all these individual cells. An even distribution across all these individual cells. So that would be 10, 10, 10, 10, 10, 10. So once again, when you're looking at this, you're looking at 3 different effects at the same time. You're looking at the effect of gender, and the null hypothesis for gender is an even distribution across the 2 groups, 30 and 30. You're looking at the effect of factory, and the null hypothesis for factory is there's an even distribution across all 3 groups, which would be 20, 20, and 20. And then you're also testing the interaction. You're also testing the interaction. And the interactions for each combination, and the null would be 10, 10, 10, 10, 10, 10. Okay, so let's look at this example. So if we were to write a chi-square test on this, first off, would we find a significant effect of gender? Almost definitely not, you're correct. Almost definitely not, because that's an even distribution in regards to gender, 30 and 30. Would we see a significant effect of factor? Correct, almost definitely not, because it's 20, 20, 20. And then when would we find a significant interaction? Almost certainly not, because it's 10 in all of them. Okay, so for this one right here, if we were to run a chi-square, do y'all think y'all would find a significant effect of gender? Probably not, you're correct, probably not. Because if you add these up, it's 30 and 30. 30 males, 30 females. Probably not going to see a significant effect of gender because it's 30 and 30. Would we find a significant effect of factor? Yeah, we probably would. We probably would get a significant effect of factory because it's 40 and then 10 and 10. That's very uneven. The null being 20, 20, 20. This is 40, 10, and 10. We probably would get a significant effect of factor. And I'll make it easy for you on this one. I'll answer the last one. We probably would not get a significant interaction because as you remember, an interaction is when the 2 variables come together and it's really one cell driving the entire effect. An interaction is when the 2 variables come together and it's really just one cell that's significantly different from all the others. In this example, we have factory that's having the effect, but it's the effect of factory A. It's not necessarily just one cell having the largest effect, it's just the effect of factory A. So in this example, we probably would not have a significant interaction, but we would have a significant effect of factory and no significant effect of gender. Okay, this one right here, would we expect a significant effect of gender? Yeah, we probably would. Yes, we probably would. Because we have, what's that, 45 males and we have 15 females. So we probably would say a significant effect of gender. Would we have a significant effect of factory? Probably not, because it's 20-20-20. And then would we have a significant interaction? Probably not, because this was driven gender. We probably would not have a significant interaction, because it's not just one cell that's significantly higher than all the others. It's just the effect of gender that's driving these differences. So we would have a significant effect of gender, not a significant effect of factory, and not a significant interaction. Okay, and then this last one, the very last one. So if we were to run a chi-square on this, do you think we get a significant effect of gender? We probably would. Would we get a significant effect of factory? We probably would. And then would we get a significant interaction? Yeah, we probably would, because it's just this one cell, this female C cell that's driving everything. So we would get a significant interaction effect. And this is something that's important to know about interactions. We'll cover this more on Wednesday. We'll cover this more on Wednesday, but we should talk about it now. And if you have a significant interaction, then that means that interaction is probably driving your, we call them main effects or direct effects. They are probably driving your direct effects. So if you have a significant interaction, that's probably driving your other significant effects. So in this case, even though we said that when we're just looking at it one at a time, that the effect of gender would be significant, the effect of factory would be significant, and the interaction was significant, it was actually just the interaction that was driving those other significant effects. So therefore, we should only interpret the interaction if it's significant, and then if your interaction is significant, you then ignore the direct effects. So once again, if your interaction is significant, you only interpret your interaction, and then you ignore your direct effects. So in this example, we see it's only that C female that's significantly different than all the others. So that indicates it's an interaction effect. So therefore, it's not factory, it's not gender independently that's doing this effect, it's their interaction. And therefore, we should only interpret the interaction effect. We shouldn't interpret the direct effect of factory or the direct effect of gender by itself. Does that make sense at all? Okay. That's really all there is to chi-square test. It's really straightforward. It's really simple. I sent you all the guide. You can do the analysis yourself. If you understood ANOVA, you should be able to understand chi-square. I think chi-square is even easier than ANOVA. But yeah, so that's all there is to chi-square. Do you all have any questions about it? Any comments about it? Yes.
Well, we're done having a quick announcement.
Yeah, sure. And we're going to be done. Well, are there any other questions? Any other comments? I think that's everything for me. Yeah, so you can make your announcement.
All right, hey everybody, my group are actually doing our survey and having it distributed and trying to run all of our analysis before next week, obviously. So we're coming up on the tail end of it. We would love if we could get a few more responses. It has gone out in the Daily Digest. But today, if you don't mind, on your way out, I have a QR code. If you guys don't mind just scanning it with your phone real quick, so we can get a few more responses, and we will be entered into a drawing as well for some lovely gifts. So if you don't mind helping us out, if you haven't done it already through the digest, just scan on your way out.
Thank you. And yeah, your group would greatly appreciate that, so please do that. Please scan, fill out the survey. It would greatly help this group. So, okay. That's all for the lecture today. If you have any questions, I'll be around for a little bit. But otherwise, you're free to go. So thank you all for hanging in there, and we will meet on Zoom on Wednesday.
have a super quick question.
Yeah, sure.
So our division, the impact of certain measurable variables on
Yes,
velocity.
yes, yes.
So we have a couple of guys that are hurt, they don't have numbers,
Okay.
but I kind of want to put their velocity away. Would that throw off the regression if the zeros ran?
So I would say leave it as blanks, because if you throw in zeros, that's gonna throw off your results, just leave it as blanks.
If it's blank, then it won't.
Yeah, then it'll be fine. Also, I saw a fascinating baseball analysis. Gosh, what is his name? I don't remember his name. There's a baseball player, I'll look it up later, where he apparently was very public like 3 years ago about your revolutions on your pitch when you're pitching. And he claimed that if anyone, had more than 100 revolutions like during a season, like in an off season, and I don't know if it's revolutions per minute or
Like
whatever.
throwing the ball to like 100.
It is.
Or like the ball spinning, like when you throw it from the mouth, like how it doesn't spin when we're getting to the plate. He argued that it might, like, if it, in the off season, someone improves by a certain amount, that would be like completely unreasonable. Now it's insinuating that player is cheating, such as like using
It might have been
I
Trout.
think that's probably, that's
He thought the Astros were cheating.
and let me give me like 1 second. I'll look it up. The interesting thing though is that so far this season, he is breaking his own rule. So he was the one who was very vocal of like, if anyone does this, it's for sure cheating.
Right.
And now his revolutions went up by that amount in the season. So now people are
I
getting
believe it.
suspicious. Yeah.
He's done really well.
See if I can find it. Yeah, Trevor Bauer. He got it.
Trevor
Yeah.
Bauer.
Yeah. Yeah, because he like talked about spin rate analysis.
Yeah.
And that's like, oh, yeah. So.
A couple of the Astros players had lower spin rates than when they got there. Like they were lower and then they got traded to the Astros and then they jumped. Like,
Yeah, yeah. So yeah, he like when that happened was all like, oh, they're definitely cheating. Like there's no way someone can improve that much. And then he improved that much this year. So
we didn't put spin rate into our
that's
just
right.
because that's more about like less about velo and velocity, more about like how it looks to you.
Yeah, yeah. So that's very nice.
Thank you.
Yes.
Yeah, so far, we're looking at on the population. So I did 21. So I think we put every tree in there. Because I want this.
How many, like, when you do the random picking?
I did 5.
How many?
I did 5 because there's only 21.
Okay. So that was your, what's your total super?
So I have.
If you get your samples size to about 30, you know, usually the cutoff for a lot of stats is like, you always want a bigger sample size. But for a lot of stats, if you have less than 30, then that like, of course, having, typically it's like 0 to 30, you definitely mess it up. 30 to like 100 to 200 is like more of a gray area. So they're more than 30.
So it's okay to like have 5 baking population.
Yeah, you know, like 15. That'd be fine. That'd be okay. Yeah, that'd be fine. Yeah.
Some of the countries 21.
I see what you're saying.
Smaller, but it does do it by calculus.
Yeah, that's by that.
Meters. So I just didn't know like people make clear, which I will do.
Yeah, as long as you get above 30, you'll be good.
And just pick them halfway.
I would say,
I think that's the best way to go. I just picked 5 random. Well, that could obviously.
yeah, I would say, I'm trying to think. I mean, if you already done it already, don't worry about it. Because I just need to go see the analysis.
Yeah. I'll just pick pretty well.
And I was gonna say, like, maybe it would be better to use like bigger countries, so like pick the top like 5 biggest countries of each category. But if you've already done it, yeah.
That's what we're trying to say. That I think that I'm trying to see if like 21 is necessarily
Better, yeah. That's an interesting research question.
We'll see how that goes.
Yeah. I'm excited to read it.
All right, thank you. Sounds good.
For like